Sonar uses sound waves to detect objects, similar to how a bat uses echolocation to navigate and detect objects. It's the same principle with seismic data for exploration of underground features. So we're going to explore this machine learning case study to use sonar to detect metal pipes underground and look at the difference between rock and this metal pipe. So we have some type of a sound source, and we're going to send out waves, and based on how those reflect at different angles, we are going to try to classify whether that is a metal pipe or if it's a rock sample. And these are just cylindrical cores. Okay, so you have a metal pipe or a cylindrical rock sample, and we collect these at angle 1, angle 2, angle 3, all the way up to angle 60. And we're going to look at this data and try to, first of all, look at the quality of the data, maybe eliminate some of the bad data rows, and then use this to also rate which angles are the most influential for detecting the pipes. So let's go ahead and just go down to, this is the web page here, and if you come down here to the case study notebook, you can get the template that we're going to use for this. So just come here to raw, and you can do save link as, and then it's going to save it somewhere where you can open up a Jupyter notebook. You can also run this in Google Colab if you don't have Python installed. Okay, so let's. This is also an example of a final report write-up. This is from a prior student who did some background, also a little bit of information on data, the models that were evaluated, and then a summary of the results. So this is a good example of what we're looking for in the end is maybe a 1 to 2 page write-up of not just the code, but also an understanding of what the results mean and why they're significant. So this is just an example of a good report write-up. I encourage you to try to model that initially, and you can put in your own information and your own observations. But in general, it doesn't have to be very long, just a couple paragraphs with a couple explanatory figures that show the results. Okay, let's get into this. For the classification, we have this URL of data, and so if you just copy this, you can open it up and look at the raw data. It's comma separated values. It's a little bit hard to see, but you can see here are the headers, and you can see that here the class is either rock or it's going to be pipe. Okay, so there's a rock or pipe letter there that we're going to need to transform into a number as well. And that's called one-hot encoding, or just find and replace. Okay, so if we come back here, you can also see, some of these. We're going to first of all start with just importing some packages that we're going to use. So the very first one that I like to import is NumPy, numerical Python. We also want to import pandas. We're going to use that in the data frames to be able to explore the data, filter, and other things. Okay, now I'm going to also do matplotlib.pyplot as PLT. So I'll just import those 3 packages. Now let's come here and go ahead and just import the data. I'm going to do read CSV, and I want to read my URL in. Now the URL was given above, and we can just paste that in. Okay, so there's my data, and if I do data head, okay, that will show me the first 5 rows. Now I can also look at a sample of the data as well, and let's just do a sample of 10 values here, and it will show, randomly picks from that data frame, and you can see the rock or the metal, R or the M. Okay, so let's come on down to the next one. We want to do some data visualization. And some of these are already provided. If you'd like to see a little bit more information on this topic, data visualization, exploration, there's some nice tutorials there that'll take you through why we're looking at the data this way. Okay, so the very first one is a box plot. We're going to use the data frame and then plot with kind equals box. And this helps us identify outliers. So for example, maybe right here we have some data that looks like it's a bit of an outlier. This is an angle 2 right here, and you can see the power that we received back. It looks like there might be some just high anomalous values right here. And also down here you might see some as well. These all don't look too far off, not major outliers, but you do see some that we may want to filter out. And the importance of this is that if you can filter out the bad data, then we're going to get better results, okay? Because outliers can greatly influence the result, especially with types of loss functions where you have a squared error. Those outliers are going to constitute a much larger proportion of how it moves the model and adjusts the predictions. Okay, so one of the other things we can do is just get rid of the subplots. So maybe I want to keep the figure size there, but let's just show a box plot with all of them on the same axis. And this is a little bit informative because you can see the spread as you change the angle from 1 up to 60. You can see that the ones very close to the detector on both sides, those don't get as much that returns back. That's like a reflection. Okay, versus the ones that maybe are directly 180 degrees across from the sample, the wave propagates through. So we want to also look and see which angles are going to be the most influential in giving us this classification between this rock and metal pipe. Okay, and you can see that some of these across, we have values of 1 for the power or the sound intensity that it receives, and some that are closer to 0. Okay, so you can see the distribution is much more in this area. So we'll look and see which ones, with a statistical analysis, which ones are most influential in helping us determine if this is a rock or metal. Okay, let's go ahead and just group by the class, because the other thing we need to look at is, with rock and metal, we want a fairly balanced data set. So if we only had, for example, 5 rock samples and 100 metal, then it would be unbalanced data or imbalanced data. And so we need to take strategies to either get more of that one type of class, because if you have a majority class, the classifier is typically going to favor that one. Now this one isn't very unbalanced, so and you might want to look at this just with a plot instead of just grouping it and printing it out as a list. Okay, so there it shows metal versus rock. It's fairly balanced here. But let's look at not just the labels, the outcome on if it's rock or metal, but let's look at the sensors and look at the correlation between these. Now here's a correlation matrix. We're going to basically take our matrix data.corr. Okay, so let me just insert a cell above just to show what that looks like. Here's our table right here, just with numerical values. And you can see there are 60, it's a 60 by 60 matrix of values. So I'll delete that one. And this is what it looks like visualized. So we have this heat map where values closer to 1 mean there's a positive correlation. And then things down in this blue area means there's a negative correlation between those. So if you look at these clusters, like right here, zooming in, you have this cluster of, 2 sensors. They're next to each other, and you can see they're highly correlated, up to about 80%. And so you'd say maybe there's not any kind of unique information here because those are 2 highly correlated results, that maybe just one of those is needed. So maybe we don't need all of these angles, all 60, maybe only 30 or fewer are required. But you can see kind of broader clusters here where these, all in this region, are somewhat more correlated, and you can see on this region as well. But these are less, okay? And so if they were all red along the diagonal, similar to this, and then uncorrelated, so this shows that these sensors right here might be more unique. There's not a strong correlation to other sensors that we see in the list. And that's going to come into, if we only are testing this in the laboratory, but out in the field we don't want to collect 60 sensors, what angles are going to be most important for detecting these. It gives us some insight that maybe these on the end and these on the end are maybe a little bit more significant. Let's do some more looking into this as well. Visualize the data a bit more. Let's generate a density plot. So this shows the distribution of each of the sensors, and we have these density plots. The thing that you want to look for in this is, really going to be outliers. If it looks like a normal distribution, or if you've got non-normal distributions, it changes the methods that we're going to use to classify. All of these look fairly good. Not a lot of skew. There's a bit of skew on these. There's kurtosis as well. If it's normal, kind of flat, there you have outliers. There's other metrics that we can use to quantify it versus just visually looking at it. Let's generate a histogram as well. Okay, so the histogram is similar to the density plot, but just discrete bins. And it gives us some similar information. All right, so you can think of maybe some additional plots or ways to visualize this that you'd like to be able to show. In this case, the data looks fairly good. There might be some outliers, like in this region, like we saw in the box plots, that we could eliminate. So if you wanted to eliminate some, you just say data, and then maybe you'd say, I just want to take all of my data where angle 51, okay, and maybe we look at angle 51. Okay, so there are some of my values for angle 51, or I could do plot and then kind equals box. Okay, just look at that one in particular. So maybe I say I only want the rows that are going to be less than 0.06 for angle 51. So angle 51 is less than 0.06. Okay, and that's going to give me a new data frame. And then if I said data equals that, then I could eliminate those values. Okay, so let's go ahead and just eliminate those from the data set. So I only want these coming down. So if I just run this one again, I'm going to copy this. I'll insert cell below, and let's go ahead and plot that again. I see I've eliminated those 2 points. So it eliminates it for all of the angles, just for those 2 rows that I've eliminated. Okay, so I filtered a little bit of the data out. You can use box plots to help you identify where the outliers are. All right, let's go to scaling the data now. So scaling the data, we're going to do that with a standard scaler, and have sklearn, and this will be pre-processing we'll import our standard scalar. And let's create our scale with the standard scalar. And then I'm going to take my x values. These are going to be the data frame where I'm going to scale and then fit transform x. Okay, and we also still need to generate x. Split those out, and then we'll look at x columns equals data dot columns, and I'm just going to take all of them except for the last one. Okay, so in my data frame, the very last one was the rock or the metal, and I don't want that one as part of my features. So let's maybe insert a cell here and just split those out. So I'm going to just take my x, okay, and I'll drop from my columns, I'm going to drop class. All right, and then let's go ahead and just look at x. So it just includes just the angles, and I don't have this very last one that's the class. All right, and if I just looked at data instead, data has this class. I've just dropped this last column right there. All right, and now let's go ahead and insert a cell below. And the other one that I want to do is take my data, and I'm going to replace any values of m with a value of 1. Okay, so metal is going to be 1, and then I can also replace any value of r. I'm going to replace that with a 0. All right, and then let's look at our data now. So you can see the class, I've used this method of encoding, and in this case it's called one-hot encoding, just replacing the 0 with a 1. All right, and then what I want to do is just take my y values. This is going to be data.class, so I can reference it this way, and then there are my y values that I'm going to use for classification. These are my labels, and these are values that I don't want to scale. Now, the angles, I do want to scale those. Those were already scaled between 0 and 1, but I'm going to scale these with mean 0 and standard deviation 1. So that one is one that I like to use just a little bit more. It limits what you can do with select k-best. You can't use this chi-squared metric. It has to be positive. So if that's the case, use a min-max if you're going to use the chi-squared for the best features. Okay, so let's come down here. I've got my x and my y values now. Okay, so here is my x data frame, and here is my y series, and now I'm going to scale these. Okay, let's see, I've got an error here, too many indices for array. So let's see if I've got data columns. Okay, let's just print out the length of that. Okay, let's see. I'm just trying to rename those so I give it the right column names. So if I just print out x, I can see those do not have the right column names. So let's just look at the length of data columns. That's 61. We just want to take everything but the last one. So x.columns. Okay, let's also look at the length of x.columns. Okay, so we just had we have 60 there. Okay, so let's see why this is not working. Try to troubleshoot this on the fly. Okay, two were indexed. Too many indices. Okay, so Okay, I think I'm going to pause this. Okay, so the error that I had here is I put a comma here. We only have one dimension on this, so let's go ahead and just put start at the beginning. That would be 0. And so this is equivalent to the syntax of 0 to -1, so it skips just the very last one. And we're going to start with 0, or we can just leave that out, and that just is a colon to -1. -1 meaning the last one, but you don't include that one, so it's a second to last one. And now we have our X, with the correct column names. Okay, so let's continue down. Let's select the best features now. We're going to go from sklearn, and this is going to be feature selection. We're going to import select kbest, and we'll say that k equals 5, and we'll do kbest equals select kbest, k equals k, and then fit transform, and we'll do x and y. Okay, so now what we want to do is for I in with column, and then we'll enumerate. We're going to enumerate all of the x columns. Okay, so these are all of the angle names. And we'll say if x column, I'll do location 0 is in. All right, so we're going to take each column in there. If it's in the kbest, and we'll say kbest, we're going to just take the very first 5 of those. Okay, so if it's in the very first 5 best features, then let's go ahead and print the column. So it said that angle 10, 11, 12, 45, and 49 are the best. But let's just look at, let's do something here. Let's go ahead and look at some other things with this. Generate a bar plot to show the significance of each one. So I'm going to insert a cell below, and let's create a new figure. I'm going to make this just a little bit bigger. Fig size equals 12 by 6. And then let's create an X label that's different than our angles. X label is going to be I for I in range. We'll start with angle 1 and go to angle 60. Okay, so there's our X label. And then let's create a bar chart with our X label. And then we're going to use the fit with scores. Okay, this is going to be our, let's see, this is going to be kbest. Okay, so we have the kbest features here. Okay, let's see. Oh, I did fit transform, but let me do fit in this case. So I'm going to do one other one. Okay, fit equals. Okay, so we'll take our best features. And so this is similar to what we just did before, but let me just make this just a little bit simpler. Okay, so I'm going to have best features equals select kbest, and we'll do k equals 5. Okay, I'll put that down here. All right, and then we can do fit equals, and then we'll do best features and do fit. So we don't need to do the fit transform, just fit, and then x and y. Okay, so then we can put in fit, and we'll get the scores for those. All right, so here are all the scores. that we have, and we use that fit.scores with the underscore, and it shows us, the higher values are more significant, and the lower values are going to be less significant. And the interesting thing is what we saw before is the ones that had the highest, between 0 and 1, those have some of the lowest significance in terms of this ranking with select K best, versus the ones that are on the closer to the emitter, those have the higher significance. So let's just go back up to the bar chart, all the way back up here. So these signals, even though they're stronger signals, they have lower significance, versus these that have the weaker signal, they have the higher significance for being able to classify between the metal and the rock. So it's kind of interesting that you look at the signal strength, the ones that are closer to where the emitter is coming, that what's reflecting is more important than what's passing through. So that makes sense. If you have different materials, you might get a different reflection. Okay, so let's keep going. We have our fit scores. Now let's go to the train test split. Okay, so now what we want to do is train classifiers. And so in this case, we're going to use from sklearn. We'll go with model selection. We'll import train test split. Then we want to split it into our X values that are test and train, and then Y train and Y test. And that's going to be this train test split. We'll give it our X and Y data, and our test size will save 20% for later for testing. And then we could also give it a random state, and then shuffle equals true. Okay, so this helps us split it into these 80 and 20, 80% and 20%. Now what we want to do is import some classifiers. I'm just going to copy in the names of these packages. Okay, so these are 8 that we're going to use. These are supervised learning methods. And then let's go ahead and just initialize the classifiers. So we're going to create these models for each one. We're going to have AdaBoost, logistic regression, naive Bayes, Gaussian naive Bayes, k-nearest neighbors classifier, decision tree classifier, random forest classifier, support vector classifier, a neural network or multi-layer perceptron classifier. And then let's create a list of these just so we can go through these fairly efficiently. Okay, so our model list is going to be all of these models. Okay, so we've created our model list. Okay, so we've created the models, the model list. Now let's go ahead and just train the classifiers. So this is nice because then we don't have to create a separate line for each of these, because now we can just say for model in model list, we're going to fit each one. Okay, so here's our fitting process. Okay, we fit all the models. And now what we want to do is just show our confusion matrix result. So this is a little bit older syntax. I'm going to upgrade it to a newer one. That one's going to be deprecated in 1.2. So let's just go with from sklearn.metrics. We'll import confusion matrix display. Okay, so this one, I'll replace this. And then what we want to do is create a new figure. Okay, so figure, let's make this bigger as well, just like we did before. We've got a lot that we're going to show on this figure. I'll make that a 14 by 8. And then let's cycle through these. So for I and model in enumerate, So enumerate returns the index I, but also the model in our model list. All right, so if we just print I and model, then we'll see these are the different ones, 0 through 7. Okay, but let's go ahead and create a new subplot for each one. And this one's going to be a 2x4, and then we'll increment it with I plus 1. So we're going to start with 1. Subplot starts with 1 instead of 0, like most of Python. Okay, I think it's just because it was a MATLAB clone, and MATLAB started with 1. So we're going to create a title, and we'll create a string out of that model name. And then let's look at the confusion matrix. And so we'll do confusion matrix display, and we'll use from estimator, and we'll put in our model, and then let's do our X test and Y test. Okay, so these are going to be our testing values, and then we'll have our axis here. Okay, and then we'll show it, plt.show. Okay, so from the estimator we fit it, and now we're going to use this to evaluate our performance, our test values. And these are the confusion matrices. On the X is our predicted label, and this is our true label. So if we predicted that it was metal, but it was actually a rock, then we had a misclassification. If we predicted that it was rock, but it was actually metal, we have this misclassification. So this is a false positive. There's a pipe there, but there isn't. And here we said there's no pipe there, but there is. And so these are the misclassifications, a false positive, false negative. And so it's better if the values are along this diagonal instead of these off diagonal values. And so if we look at the different classifiers, we can see the best ones are going to have the lowest values there. And so we can see a support vector classifier is very good. Also a multi-layer perceptron classifier, the neural network, is very good. The Gaussian naive Bayes had a lot of false negatives there. It wasn't able to detect the pipes. Okay, random forest classifier, that's also equally good to the neural network classifier. Okay, so what we'll do is write up an executive summary, max 2-page report on the results of the classifier from the Sonar dataset, report the confusion matrix in the test set, and then what are recommendations to detect pipe versus rock, the metal versus the rock values. So take these results, go ahead and just put them into your report, put in context, meaning that you identified from the visualization, from the classification, from the evaluation, and write up that report and just show what things mean. So don't just show code, don't just show data, but put in some context and some understanding. And then if you come back to the machine learning course, if you need help on any of these, we went pretty fast through this. Here's visualization. There are cleansing, filtering the data. We talked about the one-hot encoding and transforming that from an M or an R to a 1 or a 0. We talked a little bit about balance data. So there's how you cure imbalances in data. So there's many more here in the data engineering part. And then if you go down to classification, you can see each of these classifiers with a description. So there's much more information here if you need more background. This was a case study, so it's drawing a lot of these methods together to be able to solve this problem. There are also many other case studies as well, applications. We'll be adding more as well. You can see a legend here just with regression, classification, time series, computer vision. We'll add some audio in there as well. Okay, so that concludes this for the Sonar. Hope you've enjoyed this. It's It can be used for many other types. It's kind of this, seismic. There's other things you can do with these sound waves and be able to detect things like tunnels, aquifers, other things. It reflects back differently based on what's under the ground. But I hope you've enjoyed it. There's a couple additional references here if you'd like to get some additional information.